So let's probably start with the first lecture of the mini course by Michael Wheeler from University of Melbourne, who is going to talk about integrable vertex models on the cylinder. Thank you very much. And welcome to the session. And Michael, you have it. Thank you.
Thanks, Leo. So thanks everyone for coming along. So I'm going to be talking about certain families of integrable vertex models, which have been quite topical recently. And in particular, I'll be interested in studying these models when you place them on cylindrical geometries. And we're going to be looking at such quantities with respect to their connections with symmetric functions. So that's really in a nutshell, what these lectures are going to be about. Okay, so let's say a few words about what the goals of the course are going to be. So in this course, we're going to be looking at certain families of integrable vertex models, and I want to emphasize here that these vertex models are going to be what's known as fermionic. So there are also other types of vertex models which could be referred to as bosonic, but we're looking at the fermionic ones here. And probably I would say that these are not being so topical in the literature, the recent literature. They've sort of just shown up, but really, most of the literature going back in the last 10 years has dealt with bosonic vertex models. So really, there's still some new interest in these models. And because this is supposed to be a workshop about finite temperature, basically there are really two notions of a non-zero temperature which appear in these models. So first is going to be what I call an intrinsic temperature, and is going to be denoted by T here, little t. And this is an intrinsic temperature because it is sort of built into the model. So the vertex weights that we're going to see for the model, they actually just depend on this T parameter. And the reason why this can be thought of as some analog of temperature is when T goes to 0, this will just reduce to the case of free fermions. And we'll actually see that in the vertex models themselves, you end up with non-intersecting lattice paths in that particular limit. And another remark which is important to make is this T here, this is really the Q parameter that appears in quantum groups. So normally you're dealing with UQ of affine SL2, or in general affine SLN, and the Q is really to be identified with this T here. And so actually when you send T to 0, this is nothing but what's called the crystal limit in quantum groups. So this is yet another sort of sense in which you can think of T as being like a temperature. When T goes to 0, everything becomes combinatorial and freezes in a sense. And the second parameter that we're going to look at is going to be what I call an extrinsic temperature, Q. And we've also seen glimpses of this in some of the talks in the rest of the workshop. So this Q here, this is a parameter that enters via the boundary conditions of the model. More specifically, Q can be interpreted as a fugacity which is associated to windings around a cylinder. So we've already seen this kind of parameter when we looked at, for example, the periodic Shor process, which lives naturally on a cylinder, and wrappings around the cylinder give you factors of Q. And once again, when you send Q to 0, you get back down just to the usual case of non-intersecting lattice paths. So at Q equals 0, windings will become impossible, and this means that periodic Shor processes will degenerate to ordinary ones. So this is going to be the two notions of temperature, which we will see throughout these talks. And we're going to study these ideas, as I said before, really on the canvas of of symmetric and non-symmetric special functions. And we're going to look at really 4 examples. Well, I said 5 examples here, but I don't think I will have time to cover all of them. So we're going to look at the first 4 examples here. And the 2 ones that we're going to do today will be, firstly, free fermions on the cylinder. This is something that we've already seen in some of the talks. And we'll also look at the Q-Whittaker polynomials. So really, both of these cases here, these will depend on this extrinsic temperature, which is Q. And then in the subsequent lecture, we'll look at 2 other examples, and there we will see the introduction of this T parameter. So that's the plan for cover. And so there will also be some problem sets. So those will be made available, or the first problem set will be made available after the lecture today. And so, yeah, if you're interested in learning more about these things, then the kind of things that you'll learn through doing the problems. First one is proving algebraic relations of partition functions using the Yang-Baxter equation. This is really a very standard tool in this business. You'll also learn about translating between lattice configurations and tableau. This is useful, I think, for people working in algebraic combinatorics, because most of the language of symmetric functions in algebraic combinatorics is expressed via tableau and not so much via lattice path configurations. So knowing how to go from one to the other is a useful thing to be able to do. And also there'll be some combinatorial properties of the models, in particular something called color invariance. And I had also planned to talk a little bit about fusion, but again, I don't think I'll get to fusion during the course because there simply isn't enough time to cover all of this. Okay, so that's the plan. All right, so let's start just by charting the landscape of symmetric functions for people who might not be so familiar with how everything is laid out. And so I want to sort of understand, first of all, how you go from the various families that I mentioned in the goals, just so you know how everything actually works. So sort of at the base of this hierarchy, there are the sure polynomials that live down here, and they depend on an alphabet of x parameters, x1 up to xn. And we're going to look at various generalizations of the sure polynomials. So the one that we're going to be looking at today, these are what we already saw in the talk by Matteo, is the Q-Whittaker polynomials. So in particular, these introduce an extra parameter Q. On the other side of this picture, there is something called Hall-Littlewood. And these introduce this T parameter, so this other version of temperature that I was talking about. And so the degenerations to get to sure is here I should set Q equal to 0, and here I should set T equal to 0. And this will take me back down to sure. And at the top of this hierarchy, what we'll see in the next lecture are the other Macdonald polynomials. And so these depend on both parameters. And once again, if you want to get to sure, you can actually get there in 3 different ways. So one is to first set Q equal to 0 and then T equal to 0. So sort of head along this path here. Another way is to set T equal to 0 and then Q equal to 0. So then you'll head along this path. And remarkably, there is a reduction that goes straight down, which is where you set Q equal to T. And it turns out that when you do this, all of the T dependence drops out, and you can simply head straight down this path. Okay. And these little circles that I've drawn here, the reason for these is I want to say that in this circle here, these Hall-Littlewood's, which are symmetric polynomials, they're going to live in the linear span of what are called the non-symmetric Hall-Littlewood's. So really this orange circle here is supposed to denote the space of polynomials in n variables, and there's a symmetric function that lives inside of there, which are the whole elements. And likewise, the red circle here, I want to say that this, up here you have something called LLT polynomials. Now there are also non-symmetric Macdonald polynomials, and I won't be talking about those so much, but there are something called LLT polynomials. And once again, if you take the linear span of the LLT polynomials, a certain linear combination gives you the symmetric Macdonald polynomials. So this is really the sort of picture that we want to have in mind as we head through the examples in the course. But today we're going to be looking predominantly at these two cases here. All right. Okay, so I'm going to be talking about these fermionic vertex models with quite a degree of generality, and when we actually get to the examples, we'll be more specific about what's going on. So a fermionic vertex model, quite simply, this is an assignment of a complex weight to a tile. So a tile is going to be one of these elementary plaquettes that I've drawn here. And around the edges of the tile, you have 4 vectors. So let's put them in now. So this is A, B, C, and D. Okay, so A, B, C, and D, these are vectors. In particular, they're going to be binary strings of length n. So each one of these, I could think of this as a vector A1 up to AN. And each one of these A sub i's, they either take the values 0 or 1. So it's fermionic precisely because of the fact that each of these A sub i's is constrained to be less than or equal to 1. Okay, so this is the fermionic constraint. The fact that these A's cannot take a value, an integer value bigger than 1. So these are the basic objects. And every time you see a tile that looks like this, there is a mapping of that thing to a function, which is just going to be its weight. So this is going to be some complex function in general. And typically in these models, in order to be able to do anything interesting whatsoever, you have to insist on conservation through a tile. So that's what I've written here. So the conservation means that the weight of the vertex is going to be set equal to 0. You set it to 0 by hand, unless the sum of the two vectors A and B is equal to the sum of the two vectors C and D. So in other words, you can think of this A and B here, and you can think of these as being like incoming states that get fed into the vertex. And you can think of C and D as being like outgoing states that are exiting through the vertex. And this constraint just says that whatever comes in has to go out. So it's conservation. And so if you have this constraint, then you can actually think of tilings in the model in terms of trajectories of lattice paths. So to make more precise what I mean by this, let's do a little example here. So this is the example where n is equal to 3. And I've cooked up some vectors here. And so now let's look at how correspondence works. So first of all, I'm going to look at the first component of each of these vectors. And so that is going to tell me about the paths of, let's say, color red. Okay, so I look at the first entry here. So the first one, this is a 0, and this is a 1. So the 1 here corresponds with a red path that lives here, because this is the edge that corresponds with B. And likewise, I have a 1 here. So that actually means that this path turns the corner like this. Okay, so then I do the next color. So then this one here, this is a 1, this is a 1. In fact, all of them are 1s. And so in that case, you actually have all of these edges being intersected by an orange path. And finally, let's look at this one. Let's do this in green. So here, I have no path coming in from below. I have a path which comes in from here. This is the edge B, and it goes across to D. So it has to do this sort of thing. Okay, so obviously if you start drawing more and more paths, it gets a little bit messy, but this is how the correspondence between these vectors and the paths emerges. And then in order to get a tiling, you just stack these tiles now on your grid.
Sorry, Michael.
Yes.
I have a question. So do you always think that paths kiss at a vertex, or do they cross each other? Is there any convention? Is it relevant?
It's somewhat artificial to say that it's one or the other. So if you like, you can make them cross. Yeah, there's really no distinction between. I prefer to think of them as kissing because, yeah, that's just my preference. But it actually makes no difference whatsoever. So, yeah.
Okay, thank you.
All right. So we get a tiling model using these models. Okay. Now the next thing that I want to do, I want to put these models on a torus. So that's going to be the next slide. So the basic object we're going to be considering are partition functions on a torus. So this is already in quite a bit more generality than what we're going to need. But I think that this point of view is an interesting one, and I think even for some experts who have been working on such topics for a while, the idea of studying this on the torus is already slightly beyond what is normally done. So I hope that even here there are some new ideas even for the experts. So let's study this model on the torus. So I'm just going to put lots and lots of these elementary tiles now on my torus, and I will break the symmetry immediately by drawing two seams on the torus. So let's have one seam which we'll do in green, and let's say, yeah, maybe I'll do it like this. So here is going to be one of the seams, so it goes around in this direction, and the other one, let's do it like this. Okay, so then if I take the torus and I unfold it with identified edges, then I can think of these two seams. One of them is living here, and the other one is living here. Okay, so we can just, from now on, we'll just work in terms of these kind of pictures. We won't draw the torus every single time. But yeah, think of the edges here as being identified. That's really the important point. So these partition functions that we're going to look at, they're going to depend on a number of parameters. Okay, so the first parameter is going to be capital N. So capital N is going to be the number of rows that I have. So basically here there's going to be N of these, and there's going to be M columns. And furthermore, the weights that live in the ith row, so let's say this one here is the ith row. This is going to depend on a pair of complex parameters, xi, zi. Okay, so those weights are, or those parameters are local in the sense that they get assigned to that particular row. But for every single row, you have a different pair of parameters. And the final set of parameters that we'll introduce here are really extrinsic in a way. So again, they're sort of boundary conditions. So every single time we have a path of color C that crosses the vertical seam, so that's this one in red here, every time this happens in row I, we pick up a weight of alpha IC. So I want to say that there are some fugacities associated with crossing the red line. So there are some alphas that we associate with crossing this guy here. And in a similar vein, every time you cross the green line, there are some fugacities for this. So this is going to be the betas. Okay, so this is really all the parameters that we have. And using just this language, you can do a lot. So this is really a very, very general setup. And we'll see that various reductions of this leads to a lot of interesting stuff. Okay. All right, so let's start off with really the most basic that you consider here, and this is the torus partition function. Okay, so what we're going to do now is we're going to put our model on that torus, and we're going to compute the sum over all possible configurations on the torus. So configurations now means we're drawing these lattice paths. And for every single configuration that you draw, you have to work out the weight of the configuration. And so that leads to this type of sum here. So I have the sum of all path configurations. As we'll see in a second, these will necessarily have to form loops. So you sum over all loop configurations, you take the product over all of the tiles, where you compute the weight of every single tile. And then you have to work out all of the associated fugacities for the windings that pass over these seams. And so this is the object in question. And this thing here we'll call torus partition function. Okay. Now, of course, whether you can compute it or not is another matter. In fact, this kind of computation, depending on the precise model that you're looking at, this is potentially a very complicated quantity to compute. But nevertheless, this is really the object zero that you can consider. Okay, so I said here that you get loops. Okay, so you don't get paths that begin somewhere and end somewhere. And the reason for that is because you're on the torus, you have to have loops. You cannot have a path that begins and ends somewhere within the lattice, because this would violate conservation. That would mean that necessarily you have a vertex in there where the conservation is violated. So the kind of configurations that you're going to get are going to be something like this. So in general, you'll have some paths which wrap around. So it wraps around in this direction, and then maybe it makes its way back. So this, for example, would be a valid loop configuration for this particular path. But you see that you cannot have, well, all of the loops that you get are going to be non-contractible. Okay, so in particular, you cannot have contractible loops, so you cannot have something, like this. And the reason why this is forbidden is precisely because of the fact that the paths have to always go in the upright direction. So you cannot have this kind of non-contractible loop forming. All of the loops, this kind of contractible loop forming, all of the loops will have to be non-contractible. Okay. So feel free to jump in with any questions that you might have. So stop me at any point.
Okay. Hi, maybe I have a question. So it seems that in your model, you cannot really take the alpha or beta to be zero, because, or at least all of them, because then it would prevent any loop from being there, or just horizontal loops, or.
Yeah, that's correct. So in this partition function itself, if you just set all of these fugacities equal to zero, then you will prevent windings, and then you're in trouble. Yes. So you have to have fugacities at this stage. But later on, we'll see examples where you can start setting these things to zero. But first, we need a slightly more general notion of, so this partition function is not good enough, basically. We need something a little more general. But yeah. This question will soon be answered. All right. So let's now define a more interesting type of object. So if we actually want to be able to, compute something interesting, or indeed to do the kind of things that Jeremy was talking about in his question, we need something a little more general. So we need actually a way of injecting and ejecting particles from the lattice. Okay, so in other words, we need sources and sinks. And so we do this by including two new symbols in the graphical calculus. So the first symbol is going to be injection of a particle, which I will denote by a little dot here. So every time you see the little dot, it means that a path emerges from here and then makes its way. And so in terms of the lattice model, this is actually a point of discontinuity. So really, along here, the weight that you prescribe to this little tile here will assume that here you have a 1 that corresponds to a particle being present there. Whereas if I work out the weight of this tile here, it will assume that at this edge you have a 0. So it's sort of a point of discontinuity. And the insertion of such a particle along here, indeed, this breaks the winding around the torus now. Because if you have this, and this is a point of discontinuity, it means that you can no longer have a red line that wraps around. So sort of with respect to this red line, it means that you cannot wrap there anymore. And the second thing that we're going to need is a sink. So this will denote by a cross. So a cross means that a path comes in and then dies there. Okay, and once again, if you're working out the weight of this, you should think of this guy here as having a 1 at this top edge. Whereas if I work out the weight of this tile here, I should think of that edge there as having a 0. So again, it's a point of discontinuity. And again, this breaks windings around this point here with respect to the green line. Now it's important to note that even though it breaks the winding with respect to the green, you can still have other colors that wind through there. So I could still have an orange that, you know, makes its way through here and, you know, comes out like this. So this would still be perfectly fine. It's just with respect to the green that you sort of break this toroidal symmetry.
And you still keep conservation, right?
This preserves conservation because it's yeah, all of the other parts are still conserved, and now we've actually come up with a way to you know, inject and eject particles, and as long as the number of sources and sinks are equal, then this will keep the conservation. So, okay, so in terms of this now, we're going to define correlation functions. Okay, so the basic definition here is a one-point correlation function. Okay. So the one-point correlation function, so what do? So I fix two edges, E and E prime, that live somewhere in the lattice, and I'll have a notation here, D maps E to E prime. This means that a color of path D begins at the edge E and ends at the edge E prime. And we'll call this thing one-point correlation function, even though it depends on 2 points. But really, I want to think of this as the ejection of one species into the torus. So in that sense, it's like a one-point function. And so we'll just denote this with this symbol here. So this will be a correlation function. And what we compute now is, again, the sum of all configurations on the torus, but they will now be configurations such that a path begins at edge E and ends at edge E prime, a path of color D. And then you work out the object in exactly the same way as before. And we'll use the obvious generalization to p-point correlation functions. Okay. So now let's just look at a little example of how this works. So let's actually do the following. So we'll do a 3-point correlation function, and I'll do so three injections now. So let's put one here. So then we're going to be summing over paths that do this. I'll inject another one here, kind of thing, and I'll inject another one here. And maybe this one makes its way like this. And then for the ending points, let's put them, I don't know, here. It's probably not a very interesting example, so we can make it more interesting at the end. So I'll put these two here, and then these two here. And maybe the red line, let's make it do something interesting. So let's suppose that it winds here and then makes its way up to here. Okay, so this would be a 3-point correlation function. I have injection of 3 particles here, and this is the point where they leave. And everywhere else you have periodicity. you can see actually now this almost breaks the periodicity along this seam here. Okay, so already this starts to look more familiar for people who are used to studying these models in the quadrant. So if you do enough insertions along this seam here, then you'll completely destroy the periodicity, and you'll just degenerate to the cylinder actually. And if you break the periodicity up here, then you'll degenerate to the plane. So it's a very sort of general setup. Okay, so I want to remark that just with these correlation functions, you can access all of the following. So all of these are included as special cases of this formalism. So the ones we're going to look at today, we'll look at the short processes. So the correlation functions of the short process are included in this class of objects, as are the correlation functions in the periodic short processes. You also get the Hall-Littlewood, Q-Whittaker, and Jack polynomials, Macdonald polynomials, modified Macdonalds, and also super analogs. So these are polynomials that depend on 2 alphabets. Non-symmetric Macdonald polynomials are included here, and you can even do things like computing expansion coefficients between different bases of symmetric functions. And finally, and so this is something that I personally have not looked at very much, but there are also what are called cylindrical symmetric functions. And so these are symmetric functions where you really make use of the periodicity in this direction. And so this is used in something called quantum cohomology. In the works of, for example, Christian. So these cylindrical symmetric functions are included in this setup. So it's very very generic. Okay. Any questions at this point? All right. So really what we're going to be most interested in doing is destroying the periodicity in this direction. And that will take us from the torus back to the cylinder. And indeed, the topic of lecture is supposed to be fermionic vertex models on the cylinder. So, all right, so let's get into example number 1. So this is going to be free fermions on the cylinder. And I'll go through this reasonably quickly because I think that many of these things will be familiar to some members in the audience. And in particular, we will have seen things like this already in the talks by Jeremy and Gregory, and also the talk by Matteo. Okay, so sure measures and sure processes, really the two sort of fundamental properties of the sure polynomials that allow you to define such things are these two things here. So the first one, this is the branching rule. And the second one, this is the Cauchy identity. Okay, so in the branching rule, what happens, you start with an alphabet in n variables, and you express that in terms of short polynomials in n-1 variables with some branching coefficient. And the branching coefficient is very explicit. So the branching coefficient, this vanishes unless the two partitions interlace. And in the case where they do interlace, you just get x to the difference between the two partitions. And furthermore, you have identity, we've already seen, where you sum over all partitions lambda, product of two short polynomials, and you get this remarkably simple product formula. So really these two properties, I should really say the skew Cauchy identity, but you take the skew Cauchy identity together with the branching rule, you can go ahead and define Shor measures and the corresponding Shor processes that live on the measures. So what we're going to do is look for a lattice model formulation of these two identities. So we want to really take those identities and think of them now in terms of vertex models. So what we're going to do is write the one variable skew Shor polynomial in two different ways. So the first way is I use this physics notation here. So I'm going to have a ket that depends on the partition mu, and I'm going to have, sorry, this is a bra, and I'm going to have a ket here that depends on the partition lambda. And in between, I'll have this operator here, which is called half vertex operator, usually denoted gamma plus. And this thing sort of acts on the ket, if you like, and generates a sum over partitions, and then you sandwich with this partition to extract this skew-Shor function. And there'll be another formula which is very similar, where I act on this partition here with this operator, which again is a half vertex operator, and I sandwich with this partition here. And note that both of these things, they depend on this quantity here, which is the charge. So this first operator is going to conserve the charge, whereas this one will actually change the charge by 1. So, okay, I think that many of these things are familiar, but let me just say a little bit about what it actually means. Okay, so how to actually make sense of what's going on here. So let's just do some examples on the next slide, and that will make clear what exactly is a Maya diagram and what exactly is the charge. Okay. All right, so let's choose our favorite. Say m is equal to 4, 3, 1, 1. And what I'm going to do is I'm going to construct this thing as a Maya diagram. So the way I do that, we've already seen in the talk by Jeremy. So I'm going to take lots of these things now. Okay. And what I'm going to start moving them around in such a way that I actually encode the partition that I want. So first thing I want is 2 parts of size 1. So the way that I think of this is to take all of these, and I'll just shift them up, and I'll insert a little thing here. So I'll explain how the correspondence works in a second, and then I'll take the rest of them and shift these up as well. So I'll need to put now 2 of these. And finally, I'll put 1 here. Okay, so this, I claim, is the Maya diagram that represents that partition. So you should think of, sufficiently far in this direction, you have only reds. And sufficiently far in this direction, you have only whites. Okay, so what I do is I look at each red now, and I count the number of holes that sit to the left of this. So for this guy, there is exactly 1 hole which sits under it. This one, there is 1 hole. So I get 2 1s. And then this one, there are 3 holes that sit under it. So I get a 3. And then finally, this one has 4 holes that sit under it. So I get a 4. So indeed, I get 4, 3, 1, 1. So this is the Maya diagram. And in order to associate a charge to this thing, you have to draw a reference. So somewhere along here, I have to put a vertical line. And depending on where I put that vertical line, I then count the number of reds that sit to the right of this line, and I count the number of whites that sit to the left of this line. And the difference between those 2 things is the charge. So in this case, I have, looks like I have 3 reds. So I get 3 minus 1 white. So in this case, the charge C is equal to 2. So you see that really the Maya diagram is the same always. The only thing that changes is where I position this blue line. So if I move this, up to here in this case, this will change the charge by 1. So just moving this thing along changes the charge by 1 every single step. Okay. So each of those partitions that we had on the previous slide here, I want to think of them in terms of these infinite strings of red and white particles. Okay. And we're going to see now how we can actually represent these one variable skew-short polynomials in terms of vertex models now. All right, so let's go back to the vertex model formalism that we had from before, and we're going to set n equal to 1. So previously we had vectors. Just to remind you, we had a1 up to an, this sort of thing. But now we're just going to have vectors that have single component. So this is just the case n equals to 1. And the weights that I'm going to prescribe will be these ones here. Okay. So what's happening here? So first of all, we have a conservation that says that a plus b is equal to c plus d, or the weight vanishes. And then we have a second constraint here, which is going to encode a kind of exclusion between the particles. So it comes back to Leo's question from earlier. So earlier we were talking about the case where the two particles sort of kiss or touch. This indicator here is now going to forbid this from happening. And finally, I have x to the d. So this is a very simple model, very simple weights. And you get five non-trivial tiles, which I'm going to draw now. So these are the following. So I have this, I have this, and this. So these are the 5 that I can have, where the first one is empty. And the weights that I put on these, just by using this formula, weights that you get, so this is going to have weight 1, this will have weight x, weight 1, weight 1, and this will have weight x. And the final one, the one where they kiss, like this is now forbidden. So you cannot have this. So this is a 5-vertex model from statistical mechanics. It's a very, very well-known model. I think it's fair to say that it is one of the simplest integral lattice models that remains non-trivial. And by straightforward bijections, you get to more familiar objects like lozenge tilings. Okay. So this is going to be the model that we'll use to get the Schur functions. And well, you can take those weights and you can do a little transformation of them. So the reason why we need this transformation is for proving things like Cauchy identities. So we've actually already seen this in the talk by Andrew Gitlin. Actually, he was looking at the proof of Cauchy identities using precisely this kind of arguments. So what we do is we define some other weights, W star. So they're defined in terms of the original ones by this transformation here. So this parameter x needs to get inverted, and I also need to perform a complementation of the b and the d state for these. And well, if you take the formula that we had previously, so this formula, and that transformation in this model here. And this one looks a little bit different. It's the same model, but it visually is different. So you get 5 tiles again, and these are the following. So now I'm going to have, again, the empty. I'm going to have like this. Now I'll have this. And notice that now, if you actually look at the conservation property, so the conservation property has changed now. That's precisely because of this conjugation I performed here. So the conservation now says that parts want to evolve in the up left direction. So that's the reason why they're sort of heading like this now. And if you work out the weights, well, again, you get a weight of x every single time this edge here is crossed by a path. And so that tells you that the weights are just going to be, this will be 1, this will be 1, this will be x, x, and x. Okay, so these are the models that we're going to use. Really, it's the same model, but just here I've performed some transformation of the original model. Okay, so now here is the claim. So the claim is that the following identifications are valid. So we had that first expectation value in terms of the gamma plus. And we want that thing to be equal to S lambda over mu, depending on x. Maybe I should do this in red just to preserve the style. Okay, so the claim is, what I have to do here is I put a Maya diagram along the bottom. And this Maya diagram will represent the partition mu. And furthermore, it should have charge C. So along here, I'm just going to have some infinite string now. So you should think of this row as being infinite in both directions. I have this infinite row, and I put a Maya diagram along the bottom that represents the mu. And here I put Maya diagram that represents lambda, and I put here again charge C. Okay, so what's going to happen now is you have your little dots now, and they're going to evolve according to the model that we've just seen. So they're going to propagate through here, something like this. And that quantity there, when you compute it, claim is that computes precisely the skew-short function in one variable. So here I use the first set of weights, the W's. And likewise for the second one, so again, this thing should evaluate for you the skew-short function in one variable depending on y. There will also be a factor of y to the charge minus 1. And so this time what you do is you have a particle that's going to head off now along this edge here. So you're going to have this sort of thing happening. It's difficult to draw, but so again, you put the Maya diagram along the top. This is going to have correspond with mu, and it will have charge C minus 1. And likewise along here, I put a Maya diagram corresponding to lambda, and this will have charge C. And the claim is if you compute this thing here, then you'll get this expression. Okay. And both of these claims are very easily proved by just checking interlacing property on the participating partitions. So namely, these vertex models that we've cooked up, when you actually stack them together, the tiles, they actually preserve interlacing of partitions. So that's really why this works. And so out of this, you get a corollary. So the previous proposition gave us a lattice realization of the one variable skew-short polynomials. And so if you use the branching rule now over and over again, you end up now with lattice realization of the short polynomials. And both of these, well, I think certainly this one here, very well known to people. This one is a little bit exotic compared with what you usually see, but yeah, both of these very standard. So what do you end up with now? So if I take the first picture, so this one here, I have to put at the bottom empty partition, and it's going to evolve all the way up to some non-trivial partition lambda. So I have this kind of picture. So at the bottom, I'll have the vacuum, which means I have only red particles in this direction packed together, and then empty spaces after. And at the top, I'll have some partition lambda. And these things are going to trace out some paths, and these are going to be non-intersecting lattice paths. So you get nilps. And in particular, this recovers via Lindstrom-Gessel-Viano, this just recovers Jacobi-Trudy formula for the short polynomial using this picture. And the second picture is similar, except that now along this boundary, I guess I should really make these crosses. So you'll have ejection of particles along here. And yeah, so again, along here, I'll have some partition lambda. And the particles will evolve all the way across to here. And so that will give you this quantity here. And furthermore, you can see now in this picture that you can actually think about piecing these two things together. So just, joining the two things along here, and that will give you access to things like Cauchy identities. So this is the setup. All right. Okay. Any questions at this point? All right. Okay, so
I have a short remark. So in both cases there is no wrapping.
In both cases there is no wrapping. So yeah, in terms of the original picture that we had, there's no wrapping along here, and there's no wrapping along here. So if you like, all of the fugacities have been killed. Yeah.
All right. So it's an external condition that you set all these alpha betas to 0. Okay.
Yeah, everything is set to 0 at this stage. Yeah. And the reason why the quantity is non-trivial is precisely because of the fact that you can inject and eject particles there.
Okay.
Yeah. So these operators, these row operators that we have defined, so these are very standard, and they satisfy some computational options. So yeah. So in particular, the gamma pluses, they commute with each other. The gamma minuses, they quasi-commute. So this gamma minus, if you recall, one of the things it does is changes the charge of the Mie diagram. And as a result of that, they don't quite commute. You have some extra factor of x and y, but apart from that, they commute. And the important one, really the one that gives you the proof of the Cauchy identity, is this one here, where you commute gamma plus and minus, and you pick up this factor here. Okay. So all of these claims follow from Yang-Baxter equation for the model. So I haven't said anything about Yang-Baxter equation. We'll see more about this in tomorrow's talk. But yeah, you can prove all of these identities from Yang-Baxter equation. And so from this one here in particular, you can get a very easy proof of the Cauchy identity. So again, I think this is pretty standard for everyone here, but so what do we want to do? So we want to prove that I have this sum, product of two short polynomials, and I have to put in here this slightly annoying yi to the I minus 1. Okay, and this thing here, I can represent this as vacuum expectation value. So here is one vacuum, which will have to have charge n, and then I'm going to have gamma plus x1 up to gamma plus xn, and then I have gamma minus yn up to gamma minus y1, and at the end I have to put here again the vacuum, but this vacuum will have charge 0. Okay, so the claim is that sum there, I can just represent it as this thing here. You can think of, there's like an insertion of a complete set of states in the middle here that corresponds with the summation of a lambda. So then I just use this computational relation, and what I'm going to do is I'll take the gamma pluses and I'll just transfer them all the way to the end. Okay, so we can do this, and out of this, what you get now is, here is the charge vacuum, charge n. I get all of my gamma minuses now. And I get here gamma plus x1 up to gamma plus xn, and then finally this vacuum. And all of that needs to be multiplied by this product that you get from doing the commutation, which is just a product of ij from 1 up to n of this. Okay. And the final part of the argument is to compute explicitly the action of these vertex operators on this vacuum here, and likewise the action of these ones on this vacuum here. And both of those end up being trivial. So the first one just gives you a product of yi to the I minus 1, from I equals 1 to n. And the second one just gives you 1. At the end of the day, the two vacuums contract and all of it, everything evaporates, and you just end up with this. Okay, so we'll compare this right-hand side that we got here with the right-hand side that we started with, and the Cauchy identity follows immediately. Okay, so that's a very standard trick. And what I want to do now is upgrade this and put it on the cylinder. Okay, so this as well we've also seen. So this identity, this was discussed by Matteo in his talk. So the periodic Shor process is based on this Cauchy identity, where you take a product of two skew-Shor polynomials, one in alphabet x, this one in alphabet y, and you have now two sums of a lambda and mu, and there is this q to the mu now. So this q to the mu is going to enter now via windings around the cylinder. So we're actually going to get back to the cylindrical geometry. And that quantity, you can compute it, and as we've seen, you end up getting this thing here. So this is a very interesting expression. So the first quantity that you have here, this is nothing but the Euler partition function. So the original partition function for partitions. So the generating series of partitions. And this product here, this is something that looks very much like the kernel for the two-Whittaker polynomial. Okay. So how does one prove this in terms of this language? So the thing that you need here is another operator, which we call energy operator. And energy operator, you sandwich it between two partitions, lambda and mu, and it just returns you the weight of lambda times the indicator. So it has just a diagonal action on partitions, gives you the weight of lambda back. And so now you can actually, by following a similar argument, you can actually get a proof of this identity by using these half vertex operators. So again, you start off from this type of quantity here, and you represent that in terms of the half vertex operators. And it's a very similar argument now. So what you want to do, so I had actually planned to do it here, but I think I won't have enough time. So maybe at the end, if there's enough time, I'll come back to it. But the argument is simply to take these gamma pluses and push them all the way through to the end as before. And when they get to the end, you basically want to use cyclicity of the trace. So really there's a kind of trace going on here, which is encoded by this mu summation. And when you use the cyclicity of the trace, those gamma pluses will come back to where they started from, with the caveat that the argument of each one of these will get shifted up by q, because they'll have to cross this q to the energy operator here. And so if you keep doing this over and over again, you will precisely generate this, infinite QPOC hammer that you have here. And at the end of the day, there's some normalization that you have to take care of, and the normalization is precisely computed in sum over the generating series of partitions, which gives you the Euler product. So I think this computation is again pretty standard, so I'll skip it, but yeah, if you have more questions about that, then I'm happy to answer. Okay, So let's get back to the cylinder now. So this partition function, the one I was just looking at, you can think of this now in terms of an endpoint correlation function on the cylinder, except that it's a kind of twisted cylinder. So really, there is an identification of this path here is sort of forced to propagate in this direction here. So really, these two edges, this one here and this one, these are identified in this picture. And likewise, this edge here is identified with this one. So there's a kind of twisting that is happening, but up to this twist, this is precisely just, you know, an object that lives on the cylinder with paths that wrap around, and every single time they wrap around the cylinder, you pick up some Q fugacity. Now, the Q fugacity that you need is this one. So we have to get Q to the mu, Q to the weight of the partition that lives along here. So this is a partition. And so the claim is, in order to get the correct weight, what you have to do is put basically a geometric progression in Q. So the fugacities, you should choose them to be Q, Q squared, Q cubed, Q to the 4. Right? And then when you wrap around in these places here, you should recover precisely the correct weight for the partition.
Michael?
Yes.
Maybe I missed a step, but it seems that now the blue lines that exit from the top have to enter shifted on the bottom. So it looks a bit different from what the setup you presented at the beginning.
Yeah, so it's correct. So that's the remark that I made before. So if you want to make it look a bit more normal, then you should complete this thing here. So you should put this sort of thing.
Okay.
And then you need to do just a shearing of the top half.
Shearing.
So everything gets pushed across here. Then you'll just get back to the usual cylinder. So things end up looking a little bit deformed here because I wanted to make a connection with the Yang-Baxter integrability in order to prove Cauchy identity. But if all you care about are the actual configurations, then you can just work on this more normal looking cylinder. But things get deformed here because of the way that I've done it. But
I see.
and so if we look at, hopefully the example that I've done here works. So if you look at the Q to the mu weight that you expect to get here. So mu is the partition that lives along the bottom. And that partition, if you work it out, so this is a part of size 1, this is a part of size 1, and this should be part of size 2. So, yeah, looks like the example is somehow not working. But maybe I should have started at 1 instead, something like this. I'm not sure, but nevertheless, the point is this fugacity should just be a geometric progression. And if you do that, you get exactly the correct Q to the mu weight. So, okay. All right, so in the remaining time, I want to talk about something which is at least visually very similar. So this is the Q-Whittaker polynomial. So we're going to construct the Q-Whittaker polynomials as partition functions on the cylinder. But the interesting point about this construction is it looks very similar to the one we just saw for periodic shell process. But the precise connection between the two is kind of tenuous. So, well, I would have once said this, but then we saw in the talk by Matteo that there are now some new connections emerging between these cylindrical shell processes and Q-Whittaker processes. So maybe the connections are starting to form. Okay, so in order to get to this representation, we're going to take an alternative realization of the Schur polynomials. Okay. So what I'm going to do is I'm going to draw a non-intersecting lattice path configuration. And I'm going to perform some steps on this. So let's start off by drawing the configuration. So let's suppose I have now, so this will be the vacuum, the bottom, and this is going to evolve to some partition state at the top. Let's say like this. Yeah, something like that. Okay, so looking at this thing, this encodes a partition. So the partition that I get here, so this will be a 2, this will be a 4, this will be a 5, and this will be a 6. So if you think of this in terms of my diagram, that will be the partition that it encodes. And what I'm going to do now is the following. So I'm going to recolor the paths. So this first path is going to have color 1. This one will have color 2. This will have color 3, and this will have color 4. And what I'm going to do is I'm going to perform a shift now. So the jth path is going to get shifted to the left by j-1 steps. So I'm now going to attempt to do this in real time. So let's take this guy here. And oops. No, I don't want to cut. I want to just paste. So here's the first one. So the first path, I don't do anything. It stays where it is. The second one, I have to give it a different color. So that's just not behaving. Yeah, it doesn't want to do it. Okay, so I'll try and do this in without. I'll just take this thing and I have to shift it across now. So it should be something like this. So it comes here, takes 2 steps across, goes like this. I think if I've done it correctly, it would be something like that. And likewise for the next one, I shift it along, so I'll do that one in green. So that one will do something like this. Oh no. Okay. This is not going to be possible. But anyhow, you just have to carry out these steps on the picture. And at the end of the day, what will happen is all of the 1, 2, 3, 4, they'll all enter via here. So they'll all make their entrance into the lattice here. And the partition that you have along the top now, this will no longer have the Maya diagram encoding, but it will have what's called a bosonic encoding. So in other words, the path of color I exits in column lambda I. Well, okay, so actually, yeah, it should be like lambda tilde. So lambda tilde is just the reverse of the partition. So this is lambda tilde 1 up to lambda tilde n. Okay, so path of color I exits in the column lambda tilde I. So that's the kind of picture that you end up with. Okay. So you get some lattice configuration now, and it uses a new set of tiles. Okay, so no longer is it going to be just the traditional non-intersecting lattice paths with some new set of tiles. And they'll have the following properties. So the first property is that a vertical edge of a tile will be intersected by at most one path, as we had previously. And the reason for that is, you think about how a vertical edge in this picture here could be doubly occupied. Well, if it was doubly occupied, it would mean that, say, this path here, when I shift it, would have to overlap with this path here. And so that would mean that I'd actually have to have a path doing this, so that when I shift it down, it will overlap on that edge there. But that's impossible because precisely this configuration, where you have two paths kissing like this is forbidden. So vertical edges, once I do this sort of compression algorithm, vertical edges will still be intersected by just one path. But horizontal edges, they can now be intersected by several paths. And indeed, you see here, this kind of picture, these horizontal edges, they have many paths overlapping here. And the final property is that paths of different colors, they may touch, but they never cross. So you'll never have the crossing of different colored paths once you perform this kind of compression here. So it kind of preserves the non-intersecting lattice path property in a way. It's just a sort of compressed version of it. Okay. All right. So that motivates the following definition. And so we arrive at the second set of vertex weights that we're going to see in these lectures. Okay. So in order to write down the weights, I need this little definition here. So for any two vectors, x1 up to xn, y1 up to yn, which live in complex n-dimensional space, I define this quantity here. Okay, so it's basically looking at pairs of elements xi and yj such that I is less than j, and I perform a sum over all such pairs. So in terms of that, we then introduce these vertex weights. So these vertex weights, they're going to depend on vectors a, b, c, and d. So these vectors now, again, they'll be binary strings, so they'll just be zeros and ones. And I have this indicator function. So this is just conservation through the vertex. I have this indicator function here. So that indicator function, again, it prevents paths of the same color from kissing. So I cannot have paths of the same color touching each other. And the final indicator function, this is really the important one. So this indicator function, we can sort of break it down. So I have here phi of d c plus d. Now phi is just a bilinear function, so I can re-express this as phi dd plus phi dc. And this thing here, this phi dd, this is can alternatively be expressed as d choose 2, the weight of d choose 2, if you actually work it out. So what I'm requiring here is that that quantity is equal to 0. If it's not equal to 0, then the vertex weight vanishes. So what does it say? So this first thing, so it means that both of these actually have to be equal to 0, right, in order for this to hold. Now, if this is going to be equal to 0, the only possible way that can happen is if the edge d, in the picture that I have, so this is edge d here. The only way that this phi dd can be equal to 0 is if I have at most one path going through here. Okay? If I have more than one path going through there, then definitely this binomial is going to be non-zero. So that's the first thing. This just enforces that I have at most one path going through the edge d. And the second one, this enforces that paths of different colors will not cross each other. So in particular, I will never see anything like this. I will never see a path of color I that turns this and a path of color J that does this. So this is J and the other one is I. Okay, where here I is less than J. So this would produce a crossing of paths, and it is precisely this thing here that would lead to this thing being non-zero. So basically both of those two things here, this one and this one, they're precisely the properties that I wrote down before. So I said here that paths may never cross, So that's this second thing here. And I also said that vertical edges can be intersected by at most one path. And that's really the first one here. So really both of those are sort of encoding the combinatorial data. And finally, I have an x to the d. So these are going to be my weights. Okay. So now here comes the claim. So the claim is that the short polynomials, you can represent them as a partition function of the following form. So now at the bottom, I will have n different colors. And all of them will be entering in this column here. And at the top, they'll make their way to some positions. And maybe I should give these things labels as well. So this is path of color 1, 2, 3, and this is 1, 2, 3. And again, you have the condition that the path of color I exits in column lambda tilde I. Okay, so that's the boundary conditions, and in particular, all of the winding fugacities are set to 0. So I cannot have winding around here, and I cannot have winding around here. So it's just and the claim is that that thing there, you work it out. I have to put some row parameters as well. So this is x1 up to xn. Claim is that that thing evaluates the short function. Okay. So then from this, it's actually very easy to get to the QEdical polynomials. So QEdical polynomials, they look exactly the same. So
sorry, before we get to that, so let me just clarify. So the paths do not exchange colors. So imagine that 1 and 2 they do like an intersection and then an intersection again. Can I kind of swap the colors, and would this contribute to something different to the partition function?
So you want to switch, say, colors 2 and 1 at the top? Or...
No, I want to have like them cross and then cross again, like 1 and 2. They exchange and then they exchange again.
Oh, right.
So this by coloring, this gives me maybe 2 partition functions, like kissing versus exchanging.
Yeah. So I mean, you're talking about this kind of thing, right?
Yeah.
At the moment, we think of it like this. So let's say this is 2 and this is 1. And you're saying that really you would like to think of another version of this where they do something a little bit different, where this guy goes like this.
Yes.
And this guy goes like this. Yeah. So this is forbidden in the sense that here you get a vertex with a. So this is a vertex that would violate this.
Okay. Okay. Right. All right. So only one of them is allowed. Okay.
So that's kind of why. Yeah. Okay. All right. So QEdicals, it's exactly the same boundary conditions. So I just put everything exactly where it was before. And here. And here. But what changes now is the vertical winding fugacities are turned on. Okay, so previously we set the fugacities for crossing this seam, we set them to 0. Now we turn them on again. So if you wrap around here, you will pick up some fugacities, and the correct ones to choose are just these. Notice that the form of this, it looks very similar to what you get in a periodic Shell process. So in periodic Shell process, I said that you have to set those winding fugacities to a geometric progression in Q, and it's the similar sort of thing here. So again, it's some sort of geometric progressions in Q. Okay, so in particular, what this says is that the path of color C, when it winds in column J, picks up this power of Q. So, you know, previously the kind of configurations you would get here would just be planar ones. So these lines will just have to propagate something like this. They're not allowed to cross or anything like that. But now you end up with the possibility to actually loop around the cylinder. So this red one here, the red one is maybe not so interesting, but the green one can do something interesting. So it can actually wrap around the cylinder here and make its way to there. All right, so you end up with this kind of phenomenon for them to actually wrap around the cylinder, and with these fugacities. And so the claim is if you do that, you get Q-Whittaker polynomials. Okay. So I have not defined Q-Whittaker polynomials, so the theorem is sort of vacuous at this stage, but if you like, you can take this as your definition of Q-Whittaker polynomials. So yeah, this will be one of the problems on the sheet looking at this partition function. Okay. All right, so let's have the final slide. So we'll prove the theorem later. And so the proof actually ends up being easier if one goes through a sort of detour, which is via the theory of non-symmetric Macdonald polynomials. So we'll see tomorrow basically how one proves it. So we'll prove actually a more general version of this, where you don't have Q-Whittaker, but you actually have the full Macdonald polynomials. And from that, you just get Q-Whittaker statement by taking the reduction where t goes to 0. So that's that. And then I wanted to conclude with really a sort of open problem kind of question that something that has mystified me for a long time. And I hope that with the recent works that we've heard about, maybe this kind of question might be closer to being answered. So using this representation of the Q-Whittaker polynomials, it is unknown how to prove either of these properties of Q-Whittakers. So this first one, this is the branching rule, and the second one is the Cauchy identity. And neither of those identities, using this cylindrical representation, I don't know how to prove either of those. Now, I should say that using vertex models, there are available proofs of both of these, but the vertex model representation that you have to use is very different from the one that I've given here. So I would very much like to understand how to make progress on either of these using this cylindrical representation. Okay, so I think it's probably a good point to stop. So yes, we can have some questions.
Thank you very much, Michael. Let's thank Michael for the wonderful first lecture.